welcome to the deep dive. Today we're tackling a big one, linear regression. It's really a cornerstone of supervised learning. You can think of it like trying to connect the dots, maybe predicting your company's sales based on how much you spend on advertising. Our goal here is to really unpack at the core ideas, how it's used, figuring out if it's accurate, and even some more advanced stuff. Basically a fast track to getting it.
Absolutely. And it's so fundamental. It's often said that, true regression functions are never perfectly linear, but that doesn't diminish its value. Linear regression is still incredibly useful, both for understanding concepts and for practical applications. Its simplicity is actually a major strength.
Okay, right. So let's make this concrete. Say you're running a business, you've got your ad spend, data, TV, radio, newspaper, and your sales numbers. You'd naturally want to ask, okay, is there even a link here between spending and selling?
Yeah, that's the first question.
And how strong is that link? Can I actually predict future sales with this? Or maybe, is there some kind of synergy? Like, do TV and radio work better together?
Exactly. And to start answering those, we usually begin with simple linear regression, just one predictor. So we imagine your sales, let's call it Y, can be roughly explained by some baseline amount, plus some effect, manner one, for every dollar spent on, say, TV ads, which is X. So the model is basically Y equals 0 plus beta 1 times X, plus this crucial little bit, epsilon, the error term.
Oh, the error term.
Yes. It represents all the stuff we haven't measured that affects sales or just, random variation. It's a reminder that our model isn't perfect reality. It's a simplification.
Okay, so E0 and theta 1 are the true unknown intercept and slope we want to know. But we have to estimate them from our data, right?
Precisely. We calculate estimates, which we often denote with a little hat symbol like zeroin, doin, betero.
And then we can make predictions. So our predicted sales would be 0 plus euro plus whatever our ad spend X is.
Exactly. And how do we find those best estimates, Giro 1? We use a method called least squares. Think about your actual sales data points and the line our model draws. For each actual point, there's a vertical distance to the line that's a residual, or an error.
The difference between actual and predicted.
Yes. E Giro. Least squares finds the line that makes the sum of the squares of all those residuals, the residual sum of squares, or RSS, as small as possible. We square them so positive, and negative errors don't just cancel out, and bigger errors get penalized more heavily. It forces the line to fit the data as closely as possible overall.
Makes sense. You want to minimize the total squared error.
Right. And the formulas to actually calculate 1 and Giro involve the average values of X and Y from your sample data. The means X and OR.
Okay, and looking at that advertising data example where they regress sales on TV ad spend, you can see that even though it's not perfect, especially at the low end, that straight line really does, as they say, capture the essence of the relationship. That's a good starting point. But here's the crucial part. Once we have that line, those estimates, how much faith can we put in them? Are the predictions reliable? Are the coefficients, meaningful?
That's exactly the right question. Assessing the accuracy is critical. There are several key metrics we use. First, there's the standard error, or SE, for each coefficient estimate, like SE1.
Standard error.
It tells us, essentially, how much we'd expect that coefficient estimate to vary if we were to repeat the whole data collection and analysis process many times. A smaller SE means a more precise estimate.
Oh, more stable.
Exactly. And knowing the standard error lets us calculate confidence intervals. A 95% confidence interval, for instance, gives us a range of values. We can be 95% confident that the true unknown value of the coefficient lies within that range.
So it's like a margin of error for our estimate.
Pretty much. The general form is roughly the estimate plus or minus about 2 times its standard error. So lowan ani erosu SE1. For that TV advertising effect in the data, the 95% confidence interval was 0.042, 0.053. It's a pretty narrow range, suggesting we have a good handle on the true effect, and importantly, 0 isn't in that range.
Ah, okay. And that relates to the next bit, right? Hypothesis testing. Just asking, is there any relationship at all?
Precisely. We often want to test the null hypothesis, H0, which usually states that there's no relationship between X and Y. Mathematically, this means the true slope O1 is 0. The alternative hypothesis, HA, is that there is some relationship, meaning O1 is not 0.
So 0 effect versus some effect.
Correct. To test this, we calculate a t-statistic. It's simply our estimated coefficient divided by its standard error. T is 1 SC11. It tells us how many standard errors our estimate is away from 0. A larger absolute t-statistic suggests the effect is real.
And then the p-value comes in.
Yes, the p-value tells us the probability of observing a t-statistic at least as extreme as ours if the null hypothesis were actually true, i.e., if the null hypothesis were actually true, i.e., if Vor1 really was 0. So a very small p-value, usually less than 0.05, means it's highly unlikely we'd see such a strong effect just by random chance if there were no real relationship. We then reject the null hypothesis.
Okay. And for the TV ads?
The p-value was tiny, less than 0.0001. Very strong evidence against the null hypothesis. Or confident TV advertising has a significant effect on sales.
Makes sense. What about the model's overall fit?
Good question. We look at metrics like the residual standard error, RSE. It's calculated roughly as the square root of the RSS divided by the degrees of freedom, RSSN2, for simple regression. It gives you a measure of the typical size of the residuals, or the average prediction error, in the units of your outcome variable, like sales.
Yeah.
For the advertising data, the RSE was 3.26, meaning predictions are typically off by about 3,260 units of sales.
Okay, so it quantifies the typical miss.
Exactly. And then there's the famous R-squared R-over. This measures the fraction of variance explained. It's calculated as 1 RSS TSS, where TSS is the total sum of squares, basically the variance in Y, if you just use the average Y as your prediction.
So it compares your model's error to the error you'd get just by guessing the average every time.
Right. It tells you what proportion of the total variability in sales is accounted for by your model, in this case, by TV ad spending. For the simple TV ad model, the RRA was both 0.612, meaning about 61% of the variance in sales is explained by TV spending. In simple linear regression, this R is also just the square of the correlation coefficient between X and Y.
61%. That seems pretty good for just one variable.
It can be, yes. But context matters. In some fields, that's great. In others, you might need higher. You shouldn't get too hung up on just maximizing R-squared. A significant coefficient might be important even with a lower R-squared.
Right. Okay, so that covers the basics with one predictor. But usually, reality is more complex. What happens when we add radio and newspaper spending into the mix? Does it just extend the equation?
Essentially, yes. We move to multiple linear regression. The model becomes y equals 0 plus bon x1 plus b2x2 plus vpnp plus soin, where each x represents a different predictor, TV, radio, newspaper. But the interpretation of the coefficients, the budgets, changes subtly but importantly.
How so?
In multiple regression, budgets represents the average effect on y of 1 unit increase in predictor xj, holding all other predictors fixed.
Ah, holding others fixed. That's key.
It's absolutely crucial. So the coefficient for TV ads now tells us the expected change in sales for a 1 unit increase in TV spending, assuming radio and newspaper spending remain constant.
Okay, so for the advertising data, the model would be something like sales, OPS BV plus 51 HTV plus B2X radio plus 3 newspaper plus so on.
Exactly. Now, an important factor here is whether your predictors themselves are correlated. The ideal simplest case is when they're uncorrelated, like in a perfectly balanced experimental design. Then you can pretty much assess the effect of each predictor separately.
But that's rare in real-world data, right? Ad spends might be related.
Very often, yes. When predictors are correlated, say higher TV spend tends to go with higher radio spend, it becomes much harder to disentangle their individual effects. The variance of the coefficient estimates increases, meaning they become less precise. And interpreting NJA as the effect of XJ while holding others fixed becomes, as the source material puts it, hazardous.
Because if TV changes, radio probably changes too in reality.
Precisely. You can't truly hold the others fixed if they naturally move together. This is a major reason why drawing strong causal conclusions purely from regression on observational data can be misleading. Correlation isn't causation, especially when things are tangled up.
Got it. So how do we estimate these multiple coefficients, still least squares?
Yes, the principle is the same. Find the coefficients mirror, Barrow-Huzico lab, that minimize the residual sum of squares, RSS. But the math gets more complex, involving matrix algebra.
Luckily, we don't have to do that by hand.
Thankfully, no. Standard statistical software packages handle all the calculations easily. And when we look at the results for the multiple regression on the advertising data, we see the coefficients, standard errors, t-statistics, and p-values for the intercept, TV, radio, and newspaper.
And what stands out there?
Well, TV and radio both have very small p-values, highly significant, but newspaper, its p-value is really high. 0.8599.
Whoa, okay. So newspaper doesn't seem to add much predictive power once TV and radio are already in the model.
That's what this suggests. It's not statistically significant in the presence of the other two predictors. Looking at the correlation table provided in the sources confirms there are indeed relationships between these spending types.
This leads perfectly into the next big challenge. When you have multiple potential predictors, maybe dozens, how do you decide which ones should actually be in the final model? Like, is at least one predictor useful? Should we include all of them? How good is the overall fit? And how do we get the best possible prediction?
Excellent questions. To address the first one, is at least one predictor useful? We look beyond individual t-tests to the overall F-statistic. The F-statistic tests the null hypothesis that all the regression coefficients are simultaneously equal to 0, 2Ls equals 0 equals 0, versus the alternative that at least one is non-zero.
So it's a global test for the whole model.
Exactly. For the multiple advertising model, the F-statistic was 570, with a p-value way below 0.00001. This gives us very strong evidence that at least one of the predictors, TV, radio, or newspaper, is significantly related to sales. And the overall R-squared for this multiple model jumped to 0.897, meaning almost 90% of the sales variance is explained by the three predictors together.
Okay, so the model as a whole is useful, but which specific variables are the important ones? We saw a newspaper look shaky.
Right. Deciding on the best subset of variables is key. One theoretical approach is all subsets or best subsets regression. You literally fit every single possible model with every combination of predictors.
Every combination. That sounds like a lot.
It is. If you have P predictors, there are 2P possible models. With just 40 predictors, that's over 1 trillion models. Computationally infeasible very quickly.
Yeah. Okay. So what's the practical alternative?
We often use automated stepwise approaches. Forward selection is one. You start with a null model, just the intercept. Then you iteratively add the one predictor that gives the greatest additional reduction in RSS or has the lowest p-value, provided it meets some significance threshold. You keep adding variables one by one until no remaining variable provides a significant improvement.
Start small, build up. Makes sense.
Then there's backward selection. You start with the full model, including all potential predictors. Then you iteratively remove the least useful predictor, the one with the highest p-value above your significance threshold. You keep removing variables until all remaining predictors are statistically significant.
Start big, trim down.
Exactly. There are also hybrid approaches. And beyond just p-values, we often use other criteria to compare models of different sizes, trying to balance fit with complexity. These include things like Mallow's CP, AIC, a Kaike information criterion, BIC, Bayesian information criterion, and adjusted R, which penalizes our role for adding more variables. Cross-validation, CV, is also a very powerful technique where you test the model's predictive performance on data it wasn't trained on.
Lots of tools in the toolbox for model selection then.
Definitely. Choosing the right predictors is a crucial step.
Okay, shifting gears slightly. What about data that isn't numbers, like categories? How do we include something like gender or ethnicity, or maybe whether someone is a student or not, in a regression model?
Great question. These are qualitative predictors, and we handle them using dummy variables. Let's take the simplest case, a predictor with just 2 levels, like gender, male-female, in the credit card dataset example. We create a single dummy variable, let's call it 11. We might set xi if the person is female and xi is 0 if the person is male.
So it's just a 0-1 switch.
Exactly. Then the model might look like balance is 0 plus 7-1 e and a cipher. For males, the predicted balance is just 0. For females, the predicted balance is 0 plus 1. So 0 directly represents the average difference in balance between females and males in the data.
Clever. And what did the credit card data show for gender?
Well, the estimated coefficient 1 for the female dummy variable was 19.73. However, the p-value was 0.6690, which is quite high, definitely not significant. Typically, we look for 0.05. So the conclusion from this data was, perhaps surprisingly, that there's no statistically significant evidence that females tend to have higher or lower credit card balances than males once other factors might be considered.
Interesting. Okay, what if there are more than 2 categories, like ethnicity, African-American, Asian, Caucasian in that data set?
Good point. If you have a qualitative predictor with, say, L levels or categories, you create L1 dummy variables. So for 3 ethnicities, we create 2 dummy variables. We choose one category as the baseline. Let's say African-American is the baseline. Then we create one dummy variable by I1, which is 1 if the person is Asian and O otherwise, and a second dummy variable by I2, which is 1 if the person is Caucasian and O otherwise.
So an African-American person would have 0 for both dummy variables.
Exactly. They are the reference group, the baseline. The model would be balance as 0 plus Vela 1 by I1 plus No I2 plus Sawyer. Here, a 0 is the average balance for the baseline group, African-American. I1 is the average difference in balance between Asians and African-Americans, and BO2 is the average difference between Caucasians and African-Americans.
Okay, so each coefficient compares one group to the baseline. And the results.
For ethnicity in the credit card data, the coefficients for Asian 1, Muddle and NIRS 18.69, and Caucasian, Monoregal and Again 2, and Nigel at 12.50, both had high p-values. Neither was statistically significant compared to the African-American baseline balance. An important point here, the choice of which category you set as the baseline doesn't change the overall model fit. The RSS and R-squared will be the same. However, the specific coefficients and their p-values will change because they represent comparisons to a different reference group.
Right, the interpretation shifts depending on the baseline. Fascinating stuff. Now, you mentioned synergy earlier. Sometimes variables don't just have separate additive effects, they interact, right? Their combined effect is different from just summing them up.
Precisely. This is the concept of interactions. The effect of one predictor on the outcome might depend on the level of another predictor. In the advertising example, maybe TV advertising is much more effective when radio advertising is also high. That's synergy. The quote was, "Spending half on radio and half on TV may increase sales more than allocating the entire amount to either TV or radio."
So how do we model that?
We add an interaction term to the model, which is simply the product of the two interacting predictors. So for TV and radio, sales equals 71 plus 701 TV plus S2, S3 plus SRE3, TVX radio plus on. That VE3 coefficient captures the interaction effect.
And did they find evidence for this interaction in the advertising data?
Yes, very strong evidence. The p-value for the TVX radio interaction term was extremely low, less than 0.00001. Including this term significantly improved the model. The R-squared jumped from about 89.7% in the additive model to 96.8% in the interaction model.
Wow, that's a big jump.
It is. It means, as the source states, that 69% of the variability in sales that remained after fitting the additive model has been explained by the interaction term. The synergy is real and substantial.
So how does this change how we interpret the main effects, like the coefficient for TV?
It changes fundamentally. With the interaction term present, the effect of TV is no longer just MR1. The effect of a 1-unit increase in TV spending now depends on the level of radio spending. It's Vable 1 plus 3 as radio.
Ah, so the slope for TV isn't constant anymore. It changes depending on the radio budget.
Exactly. This leads to an important guideline called the hierarchy principle. It states that if you include an interaction term like TVS radio in your model, you should also include the corresponding main effects, TV and radio, even if their individual p-values happen to become non-significant after adding the interaction.
Why is that?
Couple of reasons. First, an interaction term is hard to interpret without the context of the main effects it's built upon. Second, the interaction term x1, x2 is correlated with x1 and x2, so omitting them can change the meaning of the interaction coefficient itself. It generally makes for a more interpretable and stable model.
Okay, stick to the hierarchy. And can you have interactions between, say, a quantitative variable like income and a qualitative one like student status?
Absolutely. Using the credit card data again, predicting balance from income and student status, a dummy variable, adding an income x student interaction term allows the relationship between income and balance to have a different slope for students versus non-students, not just a different intercept, average level.
So the effect of income on balance could be stronger or weaker for students.
Precisely. It allows for more complex relationships.
Which brings us to another kind of complexity. What if the relationship isn't even a straight line to begin with, even for a single predictor? Like maybe more horsepower gives better MVG up to a point, but then it levels off or even gets worse.
Right. Linear regression isn't limited to just straight lines relating x and y. We can model nonlinear effects using polynomial regression. This involves adding polynomial terms like squared terms, cubed terms, etc. of a predictor to the model. For your horsepower example predicting MPG, the model might become MPG plus 0 plus mu1 9 horsepower plus 3 horsepower 2 plus stone.
So you're adding horsepower squared as another predictor.
Essentially, yes. It's still linear in the coefficients, beta 1, 2. which is what matters for the estimation method, but it allows the fitted relationship between horsepower and MPG to be curved. And in the auto dataset example, the results showed that both the linear horsepower term and the quadratic horsepower 2 term had significant p-values. This indicates that adding the squared term provided a significantly better curved fit to the data than just a straight line.
Very cool. So linear regression is actually quite flexible. Okay, so let's try and wrap this up. Linear regression, clearly it's foundational, it's powerful, useful for prediction, yes, but also really key for understanding the relationships between variables.
Absolutely. We've seen how it works from the simple case with one predictor expanding to multiple predictors. We've talked about how crucial it is to assess accuracy using things like standard errors, confidence intervals, p-values, RSC, and R-squared. We covered handling qualitative data with dummy variables, and then looked at how interactions can reveal synergy and how polynomial terms can capture nonlinear patterns. It's a really versatile tool. Of course, there's always more depth. We didn't really get into diagnosing potential problems like outliers, non-constant variance of errors, high leverage points, or the issue of severe multicollinearity among predictors. Those are important for building really robust models. And, linear models are just one family. There are important generalizations like logistic regression for when your outcome is categorical, support vector machines, tree-based methods. Lots of places to go next.
Definitely food for future deep dives. But for now, a final thought for you, our listener. Having explored the mechanics, the strengths, and maybe some of the cautions around linear regression, how might this change the way you look at the world? How might understanding this tool, its precision, but also its assumptions and limitations, make you a more critical, more discerning consumer of information when you read news headlines, business reports, or analyses of social trends? Something to think about.